Hi, do you know how many sensors are we keeping in our pocket and how many are we wearing on our wrist? Yes, the mobile phone which we carry has at least 13 sensors and the smartwatch which we are wearing has at least 10 sensors. Today we are living in a world where sensors are integral part of our everyday life. We are depending upon sensors to know our weather, to have safe living in our homes, and for safe traveling. As we are entering in the era of Internet of Things, our dependency upon sensors is going to increase more. This lays the foundation of my today's lecture topic. Respected online guests, I welcome you all in my guest talk on the review of new and emerging sensor technologies for flow, pressure, and vibration. My name is Umair Najee Mughal, and I am a PhD researcher at Department of Physics, University of Oslo. I'll try my best to uncover some aspects of this very interesting topic. I am now turning off my camera for you to have a better view of my slides. It will be a 45 minutes talk and it is divided into 5 sections. The first section is the introduction section. This section would lay the foundation by describing sensor and micro electromechanical systems. The second section is related with pressure sensors. In this section, I will talk about both pressure physics and state-of-the-art pressure sensors. The third topic is about vibration sensors. Likewise, pressure sensors section. In this section, I will talk about vibration physics and sensors. In the fourth section, I'll talk about flow and flow sensors. The final section is about emerging sensor technologies. In this section, I'll talk about emerging materials, emerging techniques, and emerging manufacturing methods, which will incrementally improve current sensor technologies. So let's start with the first section, sensor introduction. Now, before starting discussion about sensors, it is important to understand what the transducer is. A transducer is a device which converts a signal from one physical form to a corresponding signal having a different physical form. Both sensor and actuator are transducers. A sensor is used to measure, while actuator is used to do desired work. So in broadest definition, a sensor is a device whose purpose is to detect changes in the measurand and send information as a measurement to other electronics, such as a processor. The transformation from measurand to measurement is not direct and are related with each other with a calibration curve. The output of sensors can be 4 to 20 milliamp or 0 to 5 volts. The calibration between measurand and measurement has both static and dynamic characteristics. If we assume measurand as a step input, then the measurement will try to follow the measurand. Static characteristics are related with the final state, while dynamic characteristics are related with the initial state. Let us now understand what are microelectromechanical systems. As we all know that today we are surrounded by hundreds of sensors which we even cannot see by our eye. This has only become possible due to the miniaturization of sensor technology. Microelectromechanical systems or MEMS is a process technology used to create micro-integrated devices or systems that combine mechanical and electrical components on a silicon chip. The emerging technology is nano-electromechanical system technology. Microelectromechanical systems or MEMS are fabricated using integrated batch processing techniques and can range in a size from few micrometers to millimeters. These devices have the ability to sense, control, and actuate on a microscale and generate effects on the macroscale. Interdisciplinary nature of MEMS utilizes design, engineering, and manufacturing expertise from a wide and diverse range of electrical and mechanical areas. MEMS has been identified as one of the most promising technology for the 21st century and has the potential to revolutionize both industrial and consumer products by combining silicon-based microelectronics with micromachining technology. If semiconductor microfabrication is the first manufacturing revolution, then MEMS is the second. MEMS are generally developed using three different micromachining techniques: bulk micromachining, surface micromachining, and high aspect ratio micromachining. Photolithography is generally used for microfabrication of all MEMS. Bulk micromachining is a subtractive process, while surface micromachining involves processing above a silicon-based substrate. Bulk micromachining can be done by wet etching or dry etching using silicon or ceramics. High aspect ratio micromachining is a process that involves micromachining as a tooling step, followed by injection molding or by embossing or by electroforming. It is one of the most attractive technology to replicate microstructures at a high performance to cost ratio. Technology miniaturization is not just about shrinking down existing devices. It's about completely rethinking the structure of a microsystem. Hence, there are a lot of challenges which need to be considered very carefully. Some of these challenges are: at micro and nano scale, friction is greater than inertia. Also, capillary, electrostatic, and atomic forces can be significant. Heat dissipation is greater than heat storage, and consequently, thermal transport properties could be a problem or conversely a great benefit. Tiny flow spaces are prone to fluidic blockages but can conversely regulate fluid movement. Material properties such as Young modulus, Poisson ratio, and mechanical theory such as residual stress, wear are size dependent. Integration with chip is complex and system components may not scale down comparably. Miniature devices and packaging and testing is not straightforward. Some MEMS sensors require environmental access as well as protection from other external influences. Both testing and manufacturing at micro and nano scale can be very costly if the components are not produced at high volumes. Now let's move to second section of this lecture. The second section is related with pressure sensors. In this section, I'll talk about pressure physics and then state-of-the-art pressure sensors. Pressure. Pressure is defined as force per unit area. Pascal is the SI unit of pressure, which is Newton per meter square. Atmosphere is also a frequently used unit as it is used as a reference to sea level pressure. Pressure is measured as gauge pressure, absolute pressure, or F differential pressure. Gauge pressure is measured with reference to atmospheric pressure. Pressure is positive if it is above 1 atmosphere and negative if it is below. Absolute pressure is measured with reference to absolute vacuum, that is with reference to zero value. This reference can be used when range of interest is below atmospheric pressure. Differential pressure is used to measure difference between two pressures. Now let's start with a simple pressure sensor. Mercury pressure sensor. This sensor is based on Bernoulli principle. The most simple definition of this principle is that an increase in the speed of the fluid occurs simultaneously with a decrease in static pressure or a decrease in fluid potential energy. Mathematically is represented by this equation. Here P is a pressure in a tube which can be different here and there. G is a gravitational acceleration. Y is the height of the fluid which can be different here and there. And V is a fluid velocity which can be different here and there if the fluid is moving. In this construction, a U-shaped wire is immersed in mercury which shorts its resistance with the height of mercury in each column. The resistors are part of Wheatstone bridge which remains in balance as long as the potential difference in the tube is zero. The output voltage is proportional to a difference in resistance delta R of the wire arms, which are not shunted by mercury. This sensor needs precision leveling and is susceptible to shocks and vibration. It requires large area and it is used in industrial plants. The next sensor is piezoresistive sensor. In MEMS, this sensor has two components, which are elastic silicon membrane of area A and detector, which corresponds to applied force, which responds to applied force. The detection is done by piezoresistive gauge resistors, which are made by diffusing impurities into the diaphragm. The problem with this sensing is the order of output and strong temperature sensitivity of silicon. Here pi L and sigma L are the longitudinal components, while pi T and sigma T are the transverse components. In this case, change in resistivity is proportional to applied pressure. This technique suffers from hysteresis effect and low resolution. The other type of pressure sensor is capacitive pressure sensor. Capacitive pressure sensor measure changes in electrical capacitance caused by movement of the diaphragm. A capacitor consists of two parallel conducting plates separated by a small gap. Top plate is moving silicon diaphragm, while the second plate is a fixed back plate. Entire sensor can be fabricated from a solid piece of silicon, thus maximizing its operational stability. The diaphragm can be designed to produce up to 25% capacitance change over a full range of capacitance, which make the sensor good candidate for direct digitization. Piezoresistive diaphragm should be designed to maximize stress at its edges, while capacitive diaphragm utilizes a displacement of its central portion. These diaphragms can be protected against overpressure by including mechanical stops close to either side of the diaphragm for a differential pressure sensor. These sensors are linear over the displacements, which are much less than their thicknesses. Piezoresistive and capacitive pressure sensors can be used for absolute gauge and differential measurements. Piezoelectric pressure sensors use inherited piezoelectric properties of materials. Some materials, such as quartz or especially formulated ceramics, can generate a charge across the faces when pressure is applied. A charge amplifier converts this to an output voltage proportional to the pressure. This charge is not permanent and will leak away over time. This pressure sensor can only be used for differential pressures, reference to the initial state of a piezoelectric material. In the next slide, we will see how magnetic sensor works. If the interest is to measure very low pressures, then magnetic sensor such as variable reluctance pressure can be used. In this construction, the assembly of an E-shaped core and a coil produces a magnetic flux whose field lines travel through the core, the air gap, and the diaphragm. When the diaphragm deflects, the air gap changes with respect to the direction of a deflection, thus causing the modulation of the inductance. This sensor contains two inductances, and therefore it can be realized as a half variable reluctance bridge, where each inductance forms one arm of the bridge. The air gap reluctance in the electromagnetic circle changes proportionally to the differential pressure applied. Piezoresistive, capacitive, and piezoelectric sensors are temperature sensitive and therefore requires a thermal compensation. Optoelectronic sensors, on the other hand, are not temperature sensitive. They have high resolution, high accuracy, and low interference. These sensors operate using the light interference phenomena such as Fabry-Perot interference. In the construction, this sensor consists of a passive optical pressure chip with a membrane etched in silicon, a light-emitting diode, and a detector chip. A detector chip contains three PN photodiodes. These two layers form the Fabry-Perot cavity. The operating principle is based on the measurement of a wavelength modulated between reflected and transmitted light due to the variation in the width of Fabry-Perot cavity. The width of the cavity is a linear function of the applied pressure. The detector chip works as a demodulator and generates electric signals with respect to applied pressure. The photodiode without the Fabry-Perot cavity serve as a reference diode, which monitors the total light intensity arriving at the detector. The output of the sensor is inherently nonlinear, hence a linearization by a microprocessor is generally required. Now, as we have seen that the conventional pressure sensors employ some kind of membrane, hence it is not possible for them to measure very low pressures which are close to vacuum. In the next slide, we will see how vacuum pressure sensors works without membranes and still can measure very low pressures. Now, vacuum pressure sensors are used when the aim is to measure pressure close to vacuum pressure. Hence, vacuum pressure sensors rely on some physical property of gas molecules. These properties can be thermal conductivity, viscosity, ionization, or others. The Pirani vacuum gauge is a sensor that measures pressure through the thermal conductivity of gas. It is one of the oldest vacuum sensor, but it is still in use. The simplest version of the gauge consists of two parallel heated plates. This system illustrates a sensor chamber which is divided into two identical sections. One section is filled with a gas at a reference pressure, say 1 atmosphere, and the other is connected to a vacuum that is to be measured. In this design, each heater is a thermistor whose resistances are equal. The output voltage delta V is taken differentially from the sensing thermistor and a bridge circuit. Pressure is proportional to the amount of heat loss from the plate. The amount of heat lost is measured using the change in output voltage. The other type of vacuum sensor currently in use is gas drag pressure gauge. This is a very sensitive and can measure very low pressure close to absolute vacuum. In this sensor, the gas molecules interact with a moving body. In the implementation of this sensor, a small steel ball having a diameter of 4.5 mm is magnetically levitated inside a vacuum chamber and allowed to spin with a rate of 400 Hz. The ball magnetic movement induces a signal in the pickup coil. The gas molecules exert drag on the ball and slow its rotation. The pressure is then measured as a function of density of ball, rho, the diameter of ball, A, the fractional rate of slowing down, omega dash upon omega, mean gas molecular velocity, C dash, coefficient of thermal expansion of the ball, and the ball's temperature. Let us now go to the third section of this lecture. Now we will talk about vibration sensors. In this section, I will talk about vibration physics and new vibration sensors. Let's start this section by understanding vibration. Vibration is used to measure the dynamic state of a system. Vibration is a mechanical phenomena which is based upon motion of a body or system. The motion can be periodic, aperiodic, or random motion. A displacement function, as given this, can be used to represent vibration. In this equation, x is the displacement function, k is the stiffness, and it is used to represent the amount of energy which can be recovered. M is the initial mass or seismic mass of the system, while B represents the dynamic damping or energy which can be lost. The natural frequency or say period of the system is represented by the square root k upon m, while zeta is a ratio of external damping to the internal damping or natural damping of the system. If zeta is 1, then the system is critically damped, which means it will immediately come to rest after excitation. If zeta is less than 1, it means the system will show some oscillations before coming to rest. And if it is greater than 1, it means that the external damping is greater than the damping of the system itself. The vibration can be determined directly by measuring the displacement, velocity, or acceleration. A displacement can be measured by strain gauges or eddy current, while velocity can be measured by traditional velocity sensors or piezoelectric velocity sensor. The acceleration is measured by accelerometer. The strain gauge vibration sensor measures strain of a system. The rate of strain of a system then helps to measure vibration. Strain gauges are both versatile and accurate, and also suitable for hazardous environment. But they are hard to install correctly to get proper data. The other displacement measurement technique is through eddy current. In this case, vibration is determined by detecting change in the position of a conductive component. The sensor is a probe which creates alternating current in the tip of the probe. The alternating current creates small eddy currents in the components of interest. As the field interaction changes, the sensor will produce a voltage in proportional to the displacement. Eddy current sensor required that the component be 3 times larger than the sensor diameter for normal operation. Otherwise, advanced calibration will be required. Eddy current sensor has medium accuracy and are not optimal for high resolution application. They are durable and non-contact devices, which make them good option for dirty environments. Velocity sensors are used for low to medium frequency. Velocity sensors are based upon principle of eddy current or capacitive measurements. Their advantage is direct measurement of velocity. Their disadvantage is that they veer over time owing to small moving parts and are very sensitive to mounting orientation. On the other hand, piezoelectric velocity sensors are called internally integrated accelerometers. These are most common today as they are more rugged and smaller in size than eddy current velocity sensors. Accelerometers are the most common sensors to measure vibration through acceleration. A correctly designed, installed, and calibrated accelerometer have a clearly identifiable resonant or natural frequency and a flat frequency response chain. Within this range, the output of a sensor will precisely reflect the structural dynamics. The sensitivity of accelerometer is a ratio of an electrical output to the mechanical input. It is expressed in volt per gravitational acceleration. Now in the next slides, I will go in more detail about different type of accelerometers. A piezoresistive accelerometer incorporates strain gauges to measure strain in mass supporting springs. An example of such accelerometer is shown in this figure. It was developed by Devco company. This microsensor is fabricated from 3 layers of silicon. The inner layer or the core consists of an initial mass and the elastic hinge. The mass is suspended inside an S-trim on the hinge, which has piezoresistive gauges on either side. The gauges detect motion about the hinge. The outer 2 layers, the base and the lid, protect the moving parts from external contamination. Both parts have recesses to allow the inertial mass to move freely. When acceleration is applied along the sensitive axis, the inertial mass rotates about the hinge. The gauges on both sides of the hinge allow rotation of the mass to create compressive stress on one gauge and tensile on the other. Because gauges are very short, even the small displacements produces large resistance changes. With a proper design, they can withstand shock up to 10,000 G. Shock is a high energy excitation within a short interval of time. The shock is used as critical specification for many applications. Next is the most common type, piezoelectric accelerometer. They use piezoelectric materials such as quartz or ceramics. Let's take a quartz cell which is electrically neutral under no stress conditions. When external force Fx is applied along the x-axis, the hexagonal lattice becomes deformed. Thus the crystal develops an electric charge along the opposite axis. In a simple construction as shown here, the ceramic crystal is sandwiched between the case and the seismic mass. The seismic mass exerts force on the ceramic crystal in proportional to the vibration of casing. In MEMS, piezoelectric accelerometers, a silicon chip structure is usually employed instead of ceramic. But silicon do not possess piezoelectric properties, hence a thin film of lead titanate is deposited on a micro-machined silicon. For good accuracy characteristics, a piezoelectric signal is amplified by a charge to voltage or current to voltage converter, which is usually built into the same housing as the piezoelectric crystal. These sensors typically operate from frequencies as low as 2 Hz and up to 5 kHz. They possess good off-axis to noise rejection, high linearity, and a wide operating temperature range. Next, we will see how thermal energy can be used to measure acceleration in state-of-the-art accelerometers. The other category of accelerometer are thermal accelerometers. In these sensors, heat equation is used to measure acceleration. A thermal accelerometer, such as heated plate accelerometer, contains a seismic mass, which is suspended by a thin cantilever and positioned in close proximity to a heat sink or in between two heat sinks. The space between these components is filled with thermally conductive gas. The mass is heated by a temperature or embedded heater to a defined temperature T1. Under no acceleration condition, a thermal equilibrium is established between mass and the heat sinks. The amount of heat Q1 and Q2 to the heat sinks through the gas from the mass will be a function of mass m1, distances m1 and m2. This form a relationship as like this. In this equation, lambda is a constant which is given as this. Kg is the thermal conductivity of gas, Ksi is the thermal conductivity of silicon, D is the thickness of the cantilever beam, W and L are the length and width of the beam, and P is the thermal power. To measure temperature, a temperature sensor is deposited on the beam. Eventually, the measured beam temperature in the form of an electric signal is a measure of acceleration. The sensitivity of a thermal accelerometer is smaller than that of capacitive or piezoelectric types, but it is less susceptible to interferences associated with ambient temperature, electromagnetic, and electrostatic noise. Another interesting type of accelerometer uses gas as a seismic mass. This is called heated gas accelerometer. The heated gas accelerometer was developed by MEMSIC Corporation. It is fabricated on a micro machine CMOS chip and is a complete biaxial motion measurement system. The principle of operation of a device is based on a heat transfer by forced convection. In this simple construction, under zero acceleration or no force condition, temperature distribution along the cavity is symmetrical about the heat source, and it will output zero voltage. Acceleration in any direction will disturb the temperature profile due to forced convection. This will take away the cone-like distribution asymmetrical. The differential pressure delta and thus the voltage at the thermopile outputs is directly proportional to the acceleration. The most important advantage of this sensor is a shock survival up to 50,000 G, leading to significantly lower failure rates. Now we will move to the third section, which is related with flow sensing. The third section of today's lecture is related with flow sensors. Let's start this section by understanding basic physics and then sensors. Mass is a conserved quantity. This means that the fluid mass entering a system is equal to the fluid mass leaving the system. For a fixed cross-sectional area and constant density, the fluid flow rate can be described as a product of density and flow rate or flux. Flow meters are transducers or sensors to measure flow rate, and they do this by determining the rate of change of mass or volume. The most simplest technique to measure flow rate is by installing a mechanical wheel such as paddle wheel or propeller inside a pipe. Liquid flowing through the pipe will rotate the paddle wheel. In this case, flow rate is proportional to the rotating speed of the pedal wheel. This technique has moving parts and it can be used only for low viscosity and non-contaminated fluids. It is also sensitive to vibration. It is affected by pipe size, fluid temperature, and particles in the flow. In the pressure sections, I discussed about Bernoulli principle. The equation of this principle is given as this. Here P is the pressure in the tube of flow, which is different here and there. G is the gravitational acceleration. Now in pressure sections, we discuss that Y will be different here and there. But in flow sensor, this Y has to remain the same. Also in pressure section, I just mentioned that the velocity will remain same, but in the flow sensing section, this velocity will be different here and there. Bernoulli principle therefore allows us to find fluid velocity by measuring pressure along the flow. The pressure gradient technique essentially requires introduction of flow resistance, which can be a Venturi effect or installation of porous plug in the flow. Measuring the pressure gradient across a known resistor allows one to calculate a flow rate. This technique requires the use of either one differential pressure sensor or two absolute pressure sensors. When moving mass enters a high resistance area, its velocity increases in proportional to the resistance. To determine the mass flow rate per unit time for an incompressible fluid, Bernoulli equation can be simplified to this equation. Here zeta is a coefficient which is determined through calibration. Zeta will may be different for different fluids at different temperatures. Advantages of the pressure gradient method is in the absence of moving components, use of inserted pressure sensors, and low design cost. Its main disadvantage is high pressure drop, which can be reduced by nozzle phenomena. Both pedal wheel and differential pressure sensors have low response characteristics at low flow rates. Next, I will talk about microflow sensors. Microflow sensors are gas flow sensors which are used when high frequencies are encountered in process control. These sensors operate on the principle of thermal transport. A MEM-based microsensor is shown in this figure, where titanium films with thickness of 0.1 micrometer are sandwiched between two layers of silicon dioxide. Titanium films serve as both temperature sensors and the heating element. Titanium was used because of its high temperature coefficient and excellent adhesion to silicon dioxide. Two microheaters are suspended with four silicon girders at a distance of 20 micrometer from each other. Ru and Rd are the resistances of the upstream and downstream heaters. This figure shows a simplified circuit diagram for the sensor which exhibits an almost linear relationship between gas flow and output voltage delta V. Also, cantilever design microflow sensor can be fabricated from a silicon crystal using MEMS technology. The thickness of cantilever in this case is 2 micrometer and it is heated by an embedded resistor with a rate of 20 Kelvin per milliwatt. The heat is removed from the sensor by three means: conducting through the cantilever beam, convection between cantilever and the flowing gas, and thermal radiation. This heat transport phenomena follows Stephen-Boltzmann's law. Far from the surface, the flow can be represented by using this equation. Here V is the input voltage and B is a constant. Mu is equal to this. Here L is a gas sensor contact length, N is a gas density, Cp is a molecular gas capacity, Kg is the thermal conductivity of gas, and V is the gas velocity. Using this relation, it is possible to determine flow velocity. A microflow sensor can also be constructed by utilizing capacitive pressure sensor, as shown in this figure. An operating principle of this sensor is based on a pressure gradient technique, as described by Bernoulli principle. The gas enters the sensor's housing at pressure P1 and it leaves the sensor cavity at pressure P2. The gas flows into the microsensor cavity through a narrow channel having a relatively high pressure resistance. As a result, pressure P2 inside the cavity is lower than P1, thus creating a pressure differential across the membrane. Therefore, the flow rate can be calculated by using this equation. Here K is the correction factor. V1A and V2A are the velocities before and after the resistance. Rho is the density of gas and P is the pressure. The pressure differential is measured by a capacitive pressure sensor which is composed of a thin compensated boron doped silicon membrane suspended above a metal plate. The pressure differential changes the capacitance Cx between the metal plate and the silicon structure. The output signal may be very small, which requires amplification by amplifiers integrated directly into the sensor. In the next slide, I will discuss Coriolis, ultrasonic, and electromagnetic flow sensors. Now, the next type of flow sensor is named as Coriolis flow meter. This flow meter measures flow of mass directly, as opposed to those that measure velocity or volume. A Coriolis sensor typically consists of one or two vibrating tubes with an inlet and an outlet. Tubes are set to vibrate by an auxiliary electromechanical system. The amount of twist is directly proportional to the mass through the tube. The Coriolis force induced by the flow can therefore be described as this. Here m is the mass of the fluid, omega is the rotating circular frequency, and v is the average fluid velocity. The main disadvantage of the Coriolis sensor is its relatively high initial cost. However, the versatility of Coriolis sensor in handling multiple fluids makes them very useful for plants where the flow of multiple fluid types must be measured. A typical material for a tube is stainless steel. Flow can also be measured by ultrasonic techniques. The main idea behind ultrasonic technique is to detect frequency or phase shift caused by flowing medium. One possible implementation is based on the Doppler effect, whereas the other relies on the detection of increase or decrease in effective ultrasound velocity in the medium. An ultrasonic piezoelectric sensor can be manufactured from small ceramic crystals encapsulated into flow meter body. The surface of the crystal can be protected by a suitable material such as silicone rubber. An obvious advantage of an ultrasonic sensor is in its ability to measure flow without direct contact with the flow. The transit time T of two sound between two transducers A and B can be found through the average fluid velocity relationship using this. Here C is the velocity of the fluid, velocity of the sound in the fluid. D is the distance between two opposite sides of piezoelectric ceramic crystals. And theta is the relative angle between the flow and the axis joining the two opposite ceramic crystals. Next is the electromagnetic flow sensor. The electromagnetic flow sensors are useful for measuring the movement of conductive fluids. The operating principle is based on the electromagnetic induction. When a conductive fluid crosses the magnetic flux lines, the electromagnetic force is generated in the conductor. The value of the EMF is proportional to the velocity of the moving fluid, which is given as this. Here B is the magnetic field, A is the radius of the tube, and lambda is the volumetric flow rate. Now this is the end of section related to the state of the art, pressure, vibration, and flow sensor technologies. In the next section, I will discuss about promising emerging technologies. Now this section is about emerging sensor technologies. Pressure, acceleration, and flow sensors technology will be improved if their micro and nano size components quality and performance is improved. I have therefore divided this section into three parts, which are related with emerging materials, emerging technologies, and emerging manufacturing methods. Various new materials are under consideration to be utilized in pressure, vibration, and flow sensors, such as a hollow graphene silicon composite would allow in the future to independently tune sensitivity of pressure sensor. Over the past 10 years, a number of conductive materials and composites, such as carbon nanotubes, silver nanowires, silver nanoparticles, and ionic liquids, have proven to be better options of electrode piezocapacitive based sensors. Carbon nanotubes are tubes made of carbon with diameter in nanometers. They have emerged very useful in micro and nano electromechanical systems and sensors. Good dielectric material will also enhance the performance of pressure, vibration, and flow sensors. In recent years, new dielectric materials such as EcoFlex, silver nanowire polyurethylene composites, ionotric film, graphene oxide, and carbon nanotubes will replace state-of-the-art dielectric material. For piezoelectric-based pressure, vibration, and flow sensor, polyvinylidene fluoride and its copolymers are also emerging as a promising material due to its flexibility, durability, lightweight, ease of fabrication, and chemical inertness. Beside material, it is now possible to change the sensor component, such as replacing op-amp transistor with nanoscale field effect transistors. This would add self-amplification in the piezocapacitive sensors. Also, by integrating emerging nanothermistors with these sensors, it would be possible to conduct two-dimensional measurements in future sensors. It is also possible to conduct three-axis sensing by integrating four parallel plate piezocapacitors. Using emerging nanoelectromechanical technology, it will be possible to combine the effects of two techniques, such as combining piezoresistive and triboelectric devices, or combining carbon nanotubes with capacitive pressure sensors, or combining piezoelectricity, photonic excitation, and semiconductor transport. These combinations would help to find more detail about measurand and can help to filter out unaffected variables. For micro and nano size pressure, flow, and vibration sensor, supercapacitive technology is a promising emerging technology, which can improve the sensitivity of current pressure sensors by at least 1,000 times. It can work independently in microfluidic pressure sensor or in coordination with polymer to form ionic gels. Triboelectric nanogenerator are also replacing excellent potential to harvest energy in order to develop a self-powered and vibration sensor. A digital droplet flowmetry is emerging as a promising technology to accurately monitor or control flow at very low flow rates. This technique has a possibility to discretize a continuous flow into individual digital droplets using surface tension and capillary effects. Now, from the application perspective, large area fabrication in combination with micro and nano components and batch production are highly desired. Recently, a few ultra-high resolution roll-to-roll systems have been developed, which may be used to produce next-generation high-resolution electrodes for pressure, vibration, and flow sensing. It is now possible to print fibers with a resolution much finer than the nozzle diameter by stretching viscoelastic ink and print various thickened or curved patterns with straight nozzle motions. Through electric field assisted methods such as electrospinning, it is now possible to manufacture fibers of much smaller diameters than ones made from 3D printing. Also, by introducing conductive fillers in the ink solution of the electrospinning system, it is possible to realize composite of fiber network. Near field electrospinning is also emerging for controllable deposition of carbon nanofibers in a direct, continuous, and controllable manner. Two-photon polymerization is also emerging to manufacture arbitrary three-dimensional micro and nanostructures of various materials such as polymers, hybrid materials, and organically modified ceramics and metals. I will end my lecture with Moore's empirical law, which predicts that the number of transistors on a chip will roughly double every 24 months. In 10 to 20 years, we might see one atom developments such that atomic transistors may replace chips. In the future, we might see quantum electrodynamic circuits for measuring pressure, vibration, and flow. The image on the right shows the way in the future with respect to the increased number of mechanical components and number of transistors on a microscale. I thank you all for listening to my lecture. Feel free to send me email if you have any questions.